Hello and welcome to Physics Chat Season 3. We are back and ready to do some more chatting. Physics Chat is a show where we talk to real-life physicists and ask them what it's like to be a modern-day scientist. We have lots of interesting guests lined up for you, and we are going to be talking about everything from what they are researching to the interesting stories which make them who they are. But you know, I couldn't do this alone. Joe and Fox are back with me on the hosting panel. How are you doing, and what are you most looking forward to in Season 3?
I'm doing really well, Susanna. Definitely what I'm looking forward to is while we've been off, there's been a few new members added to the team. Some of them will be appearing on camera, so watch out for them, but also some of them behind the scenes. So I'm really looking forward to all they're going to bring. How about you, Fox?
Yeah, I'm personally looking forward to all the topics. You know me, I love the physics, so get into all those juicy, interesting, complicated physics topics. And how about you, Susanna?
I'm most looking forward to asking my random questions. But first, let's introduce our first guest of the season, Professor David Wands, who researches how our universe began at the Institute of Cosmology and Gravitation. Hello, David. Thank you so much for being here, and how are you doing?
I'm very well, thank you. Great to be here talking with you.
So could you tell me how scientists believe the universe began? Did it start with a Big Bang?
Well, it certainly started in a very hot, energetic, dense state. We've got very good evidence for that. And it expanded rapidly at that time to form the very large, billions of light years across the universe that we see today. Maybe it's an infinite universe even on beyond what we can see today. But it started from a very, very energetic initial conditions, and it seems to have been set up just right so that it could expand not only to form that big, orderly universe, but on the very large scales today, but also all the structures we see in the universe today, the galaxies and stars, the planets and people. And so it seems to have been set up just right. And our idea is that there was a period at ultra high energies, even before that hot Big Bang, called inflation that set up those initial conditions.
That's really interesting, David. So you've mentioned inflation. We talked about this quite a lot in Joe Jackson's video. There should be a link in the top of the screen for that. So can you talk to us maybe a bit more about another concept you mentioned, high energy? What does a high energy universe mean? What does that mean for the particles in it?
So that's right. So we're really talking about the typical energy that particles have in the early universe compared with, say, in the present day, distant galaxies, for instance, we're seeing light that's optical. So that's got a typical energy associated with, but in the very early universe, the universe was smaller, and actually the wavelength of light is shorter. That means they've got more energy. If you go back 14 billion years, the typical particles have enough energy to break apart atoms. And if you go back to earlier and earlier times, the particles have increasingly high energies. In fact, in theory, we should be able to go back to a time when they've got more energy than the most energetic particles we can create at CERN. It's sort of like a cosmological collider experiment where you can probe energies, particles, physics at energies beyond anything we can test on Earth. So we're really exploring new physics by exploring the history of our universe.
Well, that is so fascinating. For anyone watching who hasn't seen, Susanna was able to do some exploration of CERN recently. So do watch those videos. You'll hear a bit more about what David's talking about there. So David, one thing I wanted to ask that's always confused me a bit. You talk about the fact that the universe when it was younger was smaller and is now bigger. But I've also heard that the universe is infinite. So how can it be both expanding and infinite at the same time?
Yeah, that's a good question because, infinity is infinity, isn't it? But actually, the laws of physics typically tell us about. So, and here, exploring the expanding universe, we're using Einstein's theory of general relativity. It really tells us about local physics. So it tells us about what happens to the distance between any two particles or any two galaxies, say, in our universe. So when we say space is expanding, we're really talking about the distance between objects. Of course, if you've got an infinite space, you might have an infinite number of galaxies in the universe. If we start thinking about infinities, we can get into trouble.
Infinity paradoxes, they're really cool. Could you tell us a few of those?
One of my favorites is the idea of the infinite hotel, the idea thought up by German mathematician David Hilbert. He imagined the booking problem in a hotel with an infinite number of rooms and an infinite number of guests. You can think about the problem he was thinking of is suppose you've got a very busy hotel manager who carefully books in all this. He has these infinite number of rooms, but he also has an infinite number of guests, and he carefully lines them up one by one. So you have one guest in every room. And so he's got an infinite hotel where every room is full, and he's really pleased with that he's done this complicated job. But then one more guest turns up. Suddenly, his hotel seems to be full, but nonetheless, if he thinks carefully about it, in an infinite hotel, he can still fit in that guest. And do you know how he can do that? Have you heard this paradox before?
Yes, I have heard this one before. The solution is that you ask each guest to move to the next room over, leaving the first room free. Because if there are infinite rooms, then there is always a room after the next one.
So you can always ask people to shuffle up, because no one's going to run into any problem, because they can always ask someone else to move on to make space for them. And then you fit in one more guest. So of course, if you add a finite number to infinity, you've still got infinity. You have to think differently when you're thinking about infinities.
I was mind-bending when I first came across that, so thank you.
I think that's what I'm definitely learning so far, is that thinking about infinity is hard. David, going back to maybe thinking about space being infinite, is it therefore possible for us to do, as Buzz Lightyear says, we can go to infinity and beyond?
Well, I don't think so. The trouble is, for us, there's a speed limit in the universe. That's the speed of light. So again, it's Einstein's theory of relativity tells us no object can travel faster than the speed of light. So in a finite lifetime, we can only travel a finite distance, I'm afraid. But that's okay. There's lots of interesting places to travel to, even in a finite space. Even on our finite planet Earth, there are lots of different places to travel.
What's the best place you've ever traveled to then?
Wow. Well, I've been lucky enough to travel all over the world, really. As a scientist, you get to travel to meetings, to meet people in different places, different countries. I think I've actually gone and given scientific talks in 5 different continents during my career. So, I've had a chance to travel to some great places, meet great people. My favorite place? Well, I was lucky enough to spend 3 months as a visiting professor in Japan. The city of Kyoto in Japan is the old capital there. It's a beautiful city. The temples there, the Japanese culture is fascinating. The food's great. I found Kyoto a super place to visit.
Amazing. It sounds absolutely beautiful. So if you want to go traveling, become a physicist and you'll get to travel the world.
Getting back to the actual physics, this is physics chat, as lovely as traveling is. So you talked about inflation earlier. Why is inflation the best model we have at the moment?
It seemed to give an explanation for why we have this smooth, orderly universe on very large scales from this very rapid expansion. That's seen most clearly in this cosmic microwave background radiation. It's almost uniform. It's almost the same temperature in all directions on the sky. Inflation could explain that by creating the whole of our observable universe by this sudden rapid expansion. But more than that, what I think really makes the idea of inflation compelling is that when people started thinking about quantum fluctuations that would inevitably be present even at very early times, even on very small scales in the universe, people like Stephen Hawking started thinking about this in the early 1980s. They realized that there would always be some inherent quantum fluctuations in this expansion. That would also get stretched up. These sort of microscopic fluctuations on really small scales would get stretched up to incredibly large scales, so that they would become the large-scale structure of our universe today. And the predictions they made are indeed consistent with what we've since seen in this cosmic microwave background radiation, for example. We do see slight variations in that temperature, which reflect variations in the very early universe. And that could have come from these quantum fluctuations during inflation. So it's this fascinating connection between quantum physics on very small scales, and then inflation stretches that up to become astronomically large scales in our universe.
Brilliant. Could you just give us a brief explanation of what a quantum fluctuation is?
Yeah. So the idea is, in quantum physics, you always have some inherent uncertainty. You can never pin down the position and the motion of any particle to arbitrary precision, which kind of goes against perhaps our everyday notion of that if we set up an experiment in the lab, we ought to be able to set up the initial position and velocity of a particle to arbitrary precision. But if you really get down onto microscopic scales, it turns out quantum physics says that just isn't possible. So this is the famous Heisenberg uncertainty principle. There's always an inherent uncertainty between the particle's position and its velocity. In inflation, this microscopic uncertainty gets stretched up to great big scales in the cosmos. And what we think is the case, that when we see galaxies and structure in our universe on astronomical scales today, it comes from these quantum fluctuations at very early times.
Very interesting. Thank you.
So if inflation was going on for a period of time, presumably it ended at some point. So how did that come about? When did that end?
So that's right. Inflation has to end, certainly in our part of the universe. It creates this very rapid expansion. It's from high energy fields that we don't see in the universe today. So the energy stored during inflation has to be released into particles. And that's what we need in the hot Big Bang model of cosmology.
Yeah, very cool. Thank you.
You mentioned inflation ends in our patch of the universe. Does that mean that there are patches in the universe that it hasn't ended in?
Yeah, that's possible because of these inherent quantum fluctuations. We might expect the energy to gradually evolve to lower and lower energies. That tends to happen in physics. But if you've got quantum uncertainty, then sometimes you actually can jump up to higher energy states. And so, although in our patch of the universe, we must have evolved down towards lower energies and then released the energy into the radiation of the hot Big Bang. In other parts of the universe, the fields could have evolved towards higher energies and so created more expansion. And then if you get more expansion, they could have had more quantum fluctuations. And that process could, in principle, be going on even now, but in patches far beyond what we can observe in our universe. So this wouldn't be observable to us today, but in principle, it's predicted by these ideas of quantum fluctuations during inflation. So this is goes by the name of eternal inflation and gives rise to the idea that you could have a multiverse, that is an infinite universe in size with many different patches of the universe, maybe inflation ending in different patches of the universe, but on unobservably large scales, so almost like different local patches of the universe.
So would physics be the same in each of those?
That's a good question, and honestly, we don't know, but it's possible that physics really could be very different in those different parts of the multiverse. It really depends whether what we think of as fundamental constants are absolutes everywhere in the multiverse, or whether they're the result of some part of that evolutionary process in the early universe during inflation. Even the laws of physics could be different in those different patches, vastly removed from our own universe. But there could be different physics at work there.
So you're talking about this idea of the multiverse, which I think it sounds very sci-fi. It's cool to hear that there is actually some backing to it. Does that mean there's sort of different versions of us in parallel universes?
Well, that's what people have speculated. The basic idea is that even if something seems very unlikely, if it's got a finite probability and the universe is infinite, it should happen infinitely many times. It might be very improbable to create another copy of you somewhere in the universe. But if the universe is large enough, even those very unlikely things could happen. So yeah, maybe that's the speculation. This is one of those problems with infinities that you get into if you take them far enough. Very paradoxical things seem to happen.
Okay, so now it's time for my random question, which this leads nicely onto. Would you like to meet a parallel universe version of yourself? And if so, what would you ask them and why?
Yeah, I don't know. It would be a bit weird, wouldn't it? but as a scientist, I think it'd be fascinating as well. If they were a scientist too, I'd love to ask them about about the laws of physics in their universe. You could actually do some fascinating physics experiments with that parallel version of yourself.
Amazing. What about you, Fox? Would you like to meet your other version?
I was thinking, and maybe. So if you met another version of yourself and they had made all the exact same life choices, then it would be fairly conclusive for determinism frame of the universe. Whereas if they had made completely different life choices, then it would be fairly conclusive for free will, I would assume.
Wow, that's very interesting. What about you, Joe?
I just want to meet a parallel universe version of the Field of View team who are doing a show called like Chemistry Talk or something, and just go through all the different, like, what could they be talking to scientists about chemistry? That'd be really weird to hear us talking about.
It's been so interesting hearing all about how scientists believe the universe started and the crazy idea of the multiverse. Who knows, me and the other universe could be quite reserved and shy. But let us know in the comments section, would you like to meet a parallel universe version of yourself? If so, what would you like to ask them and why? We would love to hear from you, so keep writing. Gosh, I haven't said that in a while. Anyway, from everyone at Field of View, we hope you have a great day and goodbye. Bye.
Bye.
Even on our finite planet Earth, there are lots of different places to travel.